So, welcome to the tutorial. In this tutorial, we'll learn how to solve different numerical problems based on LSM method in a singly reinforced beam section. So, here is a type of problem which says RCC beam of cross-sectional area 300 into 700 mm is reinforced with the 3 bars of 20 mm dia, and the effective depth from the bottom of the beam to the reinforcement center of the reinforcement is 50 mm, whereas the effective span of the beam is 6 meter, which is given in the question. So here they have asked us to adopt M20 concrete grade and Fe415 steel grade. So the very first question they have asked us to calculate or determine is to find out safe uniformly distributed load or the superimposed load that beam can carry. This is the first problem. So we'll see one by one every problem. So I have already written some given quantities here. The dimensions are given as B is 300 mm and overall depth of the beam is 700 mm, and so from here we can calculate effective depth of the beam. That one can be calculated from overall depth. We can subtract overall depth and the effective cover of the beam, which is 700 mm and 50 mm. So which will provide us the quantity, the value 650 mm. So this will be our effective depth of the beam, and as mentioned in the question, the effective span of the beam is 6 meter. So from here, we'll calculate two quantities, which are one is XU max and second is XU. So this one is the maximum depth of the neutral axis, and this one is the actual depth of the neutral axis. So the actual depth of the neutral axis can be calculated by using this formula 0.87 Fy into AST upon 0.36 FCK into B. From this formula, the given quantities are this one Fy, FCK, and B. AST we have to calculate. So for calculating AST, as mentioned in the question, we have 3 bars of 20 mm dia. So we'll calculate the area of 1 bar and we'll multiply it with 3 bars, 3 number. Okay? So from here we can calculate the total area of steel in tension, which comes out to be 942.5 mm square. So we use it in this formula. So the values are 0.87 as mentioned in the question into 415, that is the steel grade, and into the area of the steel in tension, which is calculated previously 942.5 divided by 0.36 into 20. 20 is the FCK value into 300. So this comes out to be 157.5 mm. Whereas we can calculate XU max, which comes out to be which can be calculated using this formula 0.48 into D. D is the effective depth of the beam. So by multiplying these both quantities, we'll get the value 312 mm. So basically, from here we can see that XU max value is greater than actual depth of the neutral axis. So from here we can conclude the beam section is under reinforced. So in under reinforced section, as we know that the steel is the weaker part, so we'll calculate mu, the ultimate moment of resistance for steel in tension zone. So the value of mu is 0.87 Fy into AST bracket D minus 0.42 XU. We'll plot all the values here, and what we'll get 0.87 into Fy. Fy value is 415 into area value is 942.5, and the effective depth of the beam is given, or we have calculated, which is 650 mm minus 0.42 into XU value that we have calculated previously as 157.5. So by calculating all the work quantities, we'll get the value 198,678,000, which can be also written as 198,678 kilonewton meter. So So as we have calculated this mu value, and as we all know that mu is MOR, moment of resistance. And what is moment of resistance? Moment of resistance is the maximum bending moment value that a section can resist. Therefore, as given in the question, there is a beam, simply supported beam, which is supported from both sides, is having a UDL, sorry for the drawing, which has a value which we don't know, WU, kilo, WU, Newton per meter. The span of the beam is 6 meter. So, as we all know that the factored bending moment value for a simply supported beam carrying a UDL is WU L square by 8. So from here we can calculate a value that comes out to be 6 square into WU upon 8, which comes out to be 4.5 WU. So by equating this value with this one, equation 1 and equation 2, we'll get what we'll get is equating equation 1 and 2, we get, why are you equating these values, equation 1 and equation 2? Why are we equating these values? Because MOR is nothing but the maximum bending moment value that a section can resist. So as we have already calculated a MOR value, that is this one. So maximum bending moment value we can calculate for a conditioned load for a simply supported beam through this formula WU L square by 8. So as we have one unknown value, so we can calculate by comparing both the equations and find out the value of factored load. So which comes out to be 198.678 is equals to 4.5 XU or WU, sorry, here we have WU, not XU. So the value of WU comes out to be 44.151 kilonewton per meter. As we all know that now this is the overall weight of the beam. So as we know that the self weight of the beam can be calculated by W. Let's say WV is the self weight of the beam. So self weight of the beam can be calculated by multiplying unit weight into volume. So for RCC we have unit weight value as 25,000 and the width and the height, width and the depth of the beam is already given, and we'll consider a unit section. So 25,000 into volume is given. Volume is B into D into H. H is unit, so unit quantity, which is equal to volume. So the depth of the beam is 300 mm. 300 divided by 1000, because the previous values are in meters, so we are converting it into meter directly from here only. 700 divided by 1000 into 1 into 25,000. Okay, so this value comes out to be 5250 Newton per meter. Now factored beam, factored self weight of beam is equals to, we'll multiply this one with the 1.5, which comes out to be 7875 Newton per meter. Now in order to calculate the value of superimposed load, will simply subtract this value from this value. So the values are 4 4 1 0 1 151 4 151, as this value is in Newton, so this comes out to be 36276 Newton per meter. Now, one more thing that was asked in the question is calculate the safe UDL or the safe superimposed load on the beam. So we'll do nothing. We'll divide this value, this one, 36,276 by 1.5. 36,276 by 1.5, which comes out to be 24,184 Newton per meter. So this is the first part which we have completed, is the calculation of safe superimposed load on the beam. So the second part of the question asks us to find out the central concentrated load that beam can carry in addition to its self weight. So as we already know that this beam is already imposed with a UDL, and it's saying that place and concentrated load at the center of the beam, that is in this diagram we had a UDL already acting on the beam. So the question is asking that place a point load of PU at the center of the beam. So the length remains the center of the beam. The length of the whole beam is 6 meter. There's no new concept in this. We'll just equate the MOR value with maximum bending moment due to UDL plus maximum bending moment due to concentrated load. As we all know that when we apply a UDL on a simply supported beam, the maximum bending moment value that comes out to be WL by 4. So we'll add this WL by 4 to the previously calculated bending moment value, that is MOR is equal to WU into L square upon 8 plus, now what we'll do is we'll factor the load. So 1.5 into PU into L upon 4, and here MOR value is 198,678. Okay, so let's just place the value here only, 198,678. So, and this WU is 785, so also place the value here only, 7875. L square value is 6, here also 6, 36, and here 6. So from here, from the equation, the PU value will come out to be 163,240.5 upon 2.25. Okay, and the final value for the concentrated load, that will come out to be 72,551 Newton, or if you want to write in kilonewton, then 72.5 kilonewton. So this is the concentrated load that the beam can carry in addition to the UDL which is already acting on the beam. So that's all for the today's session. We'll meet in another video in next session. Till then, stay tuned and do subscribe the channel for more updates. Thank you.